Hey everyone, and welcome to this explainer. So, you know that feeling when you're just staring at a sprawling, complex calculus problem? You're calculating limits by hand, filling up half a page of notebook paper, and thinking, there has got to be a faster way. Well, you are in exactly the right place. Today, we're going to totally bypass those tedious parts of calculus and unlock the fast, elegant rules of differentiation.
But first, to really get why calculating acceleration and rates of change matters out in the real world, just look at the Hennessy Venom GT. Back in 2014, this car reached a mind-boggling, record-setting 270.49 miles per hour. I mean, it can go from 0 to 200 miles per hour in just 14.51 seconds. The calculus techniques we're looking at today, they're the exact mathematical tools you'd use to calculate the precise acceleration the Venom achieves during that incredible run. So calculus isn't just a bunch of numbers on a page. It's literally the language of motion. It's absolutely crucial for engineering, physics, and even business analysis.
Here's our game plan for today. First, the differentiation shortcut, then the sum and difference rules, followed by mastering the product rule, conquering the quotient rule, and finally, a step-by-step derivative guide.
All right, let's jump right into part 1, the differentiation shortcut, from tedious limits to fast formulas.
Now, this perfectly illustrates the problem versus the solution. Over on the left, we've got the snail pace difference quotient. You know the drill, plugging in x plus h, expanding out binomials, canceling a bunch of terms, and taking a limit as h approaches 0. Is it foundational for understanding what a derivative actually is? Yes, for sure. But as a daily tool, it's just way too tedious. Then on the right, we have the lightning bolts, clean, elegant algebraic shortcuts that get us the exact same answer in a fraction of the time. We're going to start building our toolkit with the most foundational tool of all, the constant rule. It simply states that the derivative of a constant function, say f of x equals 8 or -3, is exactly 0. And if you think about it, why wouldn't it be? Picture a constant function on a graph. It's a perfectly flat, horizontal line. Since a derivative measures the rate of change, and a horizontal line literally never changes, its slope is a perfect flat 0.
Next up is our absolute workhorse, the power rule. Notice how mechanical and visual this process is. If you have a variable x raised to a power, n, that exponent simply drops right down to the front to become the coefficient. Meanwhile, your new power on the x decreases by exactly 1. So if you have x to the third power, the 3 drops down to the front, and the new exponent becomes a 2. Boom, the derivative is simply 3x squared. No limits, no massive fractions to simplify, just one quick, easy step.
Moving right along to section 2, the sum and difference rules, combining basic derivatives. The sum and difference rules are fantastic because they essentially give us permission to just take the derivative of each individual piece of a function when they're added or subtracted together. You don't have to look at some massive polynomial as one terrifying object anymore. You can treat it as a collection of small, easy-to-manage parts. You literally just walk down the line, taking the derivative of term 1, then term 2, then term 3, and then you just add them all up. Let's look at this in practice with a really clear example. Say we want to find the derivative of the function f of x equals 2x to the 5th power plus 7. First, the sum rule tells us we can look at the terms totally separately. So for the first term, we use the power rule. The 5 drops down, multiplies with the constant 2 that's already sitting there, giving us 10. The exponent reduces by 1, leaving us with x to the 4th. So that first chunk becomes 10x to the 4th. Then we glance over at the second term, the plus 7. Using our constant rule, the derivative of a constant is just 0. Put the whole thing together and our final result is 10x to the 4th. Just by stacking these basic rules, we quickly get our derivative without ever touching a limit table. Okay, let's step it up in section 3, mastering the product rule, handling multiplied functions. Before we jump into the rule itself, we got to address a really common trap. You might be wondering, is the derivative of a product just the product of the individual derivatives? It is incredibly tempting to assume this is true, mostly because it worked out so beautifully for addition and subtraction, but it completely fails for multiplication. Think about a super simple function like x squared. We know from the power rule its derivative is 2x. But if we split x squared into x times x and just multiply their individual derivatives, which are 1 and 1, we'd get 1. And 1 absolutely does not equal 2x. So scratch that idea. That pattern is a trap. Instead, we have to use the product rule. This rule carefully balances the two functions and their derivatives using a very specific addition structure.
If you're differentiating a function that is f of x multiplied by g of x, here's how it goes. You take the first function, leave it exactly as it is, and multiply it by the derivative of the second function. Then you add the second function, left as it is, multiplied by the derivative of the first. So first times derivative of the second, plus second times derivative of the first. Let's see how this works in action. We have two binomials multiplied together here. So the absolute most crucial thing is to clearly identify your two functions before doing anything else. Step 1, we label our first chunk f of x and our second chunk g of x. Step 2, we take the derivatives of each chunk individually using that power rule we already learned. Step 3, we plug them into our balancing equation, the original f times the new g prime plus the original g times the new f prime. Finally, step 4, it just becomes a standard algebra problem where we expand and combine our like terms to get a nice, clean polynomial derivative.
Next up, section 4, conquering the quotient rule. Differentiating divided functions.
Now, the quotient rule might look a little intimidating at first glance, but it actually shares some DNA with the product rule. For a top function f of x divided by a bottom function g of x, the derivative is the bottom function times the derivative of the top minus the top function times the derivative of the bottom. Because division is involved, this rule uses subtraction in the numerator rather than addition. And finally, you take all of that and divide it by the square of the original bottom function.
Here is the single most important takeaway for this structure. You must follow this exact order of subtraction in the top half. With the product rule, addition is commutative, so order didn't strictly matter. But here, if you swap the terms and do the top times the derivative of the bottom first, your resulting slope will have the completely wrong sign. A really classic way to remember the right order is the old rhyme, low d high minus high d low, draw a line and square below.
Finally, let's wrap up with section 5, step-by-step derivative guide, putting it all together. When you're staring down a giant calculus problem, panic is the enemy. A great rule of thumb when dealing with massive rational functions that combine a bunch of different rules is to apply your differentiation rules in the reverse order of how you would evaluate the function algebraically. Just ask yourself, what's the very last mathematical operation I'd do if I were just plugging a number into this for x? If the last thing you do is divide a massive numerator by a massive denominator, then hey, the function is fundamentally a quotient, and the quotient rule is your starting point. You set up your big quotient rule framework first, and then apply your smaller power or product rules as you figure out the inner parts of the numerator and denominator. Basically, work from the outside in. So now that you've totally mastered polynomials and rational functions using these shortcuts, I want to leave you with a final thought. How do you think these exact same differentiation rules apply to the wilder parts of math? Imagine how these very same tools, the product rule, the quotient rule, are used to unlock the chaotic waves of the ocean using sines and cosines, or even the explosive exponential growth of a viral trend. The foundation you've built today applies to all of it. Thanks so much for joining me on this explainer, and keep practicing.